In this class, we are going to analyze how various crystal directions and planes are identified and how can it be represented using some standard notations known as Miller indices. In the first lecture, we have seen that the position vector of any lattice point with respect to an arbitrary origin can be specified by an expression of this kind. We use a slightly different notation while talking about Bravais lattices. Every point of a Bravais lattice can be reached from the origin by a translation vector of the form THKL, which is equal to HA plus KB plus LC, where A, B and C are the lattice vectors and H, K and L are some integers called the Miller indices. Let's consider a two-dimensional lattice for simplicity. Here A and B are the lattice vectors along the x and y directions respectively. Let's choose an arbitrary origin O in the lattice. Then any lattice point like this one can be represented by 2a. For example, this one can be represented by 2a minus 1b. If lattice parameters are used as units of lengths along the respective axis, then lattice coordinates can simply be represented by the number 2 and minus 1. These numbers are called the site indices, and this is usually written in the form 2 1 bar in square brackets. For negative index, a minus sign is written usually above the index. Apart from this vector, a set of vectors parallel to this one can also be represented by the same indices. Now let's see how to get the Miller indices for specifying directions. To specify a direction in the crystal lattice, a straight line passing through the origin is chosen. Then the indices of the first lattice point is given as the Miller indices of that direction. First step to get the indices of direction is to note down the coordinates of lattice site nearest to the origin in a given direction. In this case, it is 1a, 1b and 1c. Next, we divide the coordinates by appropriate unit translations. Then put the resulting integers in a set of square brackets HKL to get the required indices of its and all parallel directions. However, if fractions result when we divide the coordinates by a lattice constant, then you have to multiply each of them by the smallest common divisor. For example, instead of 1, 1, 1, if you get something like 1, 3 by 4 and 1 by 2, then it will become 4, 3, 2 by multiplying all those three numbers by the common divisor 4. Some other basic directions are also shown here. See, this 1, 0, 0 is a direction along the x direction of the crystal axis, and 0, 1, 0 is a direction along the y axis, and this particular direction shows 1, 1 bar, 1. I hope you can easily understand how to get these indices for this particular direction, because this is oriented along the negative y direction. Then this particular one is called 1 bar 1 1 because it is along the negative x direction. It actually starts from not at the origin but one unit shifted in the x axis. It is possible to have an infinite number of directions in a crystal. Out of these, the set of directions having identical spacing between the atoms are called equivalent directions, and they all are always related by symmetry operations. These set of directions are expressed in angled brackets HKL. For example, the 110 family is shown here. All these directions actually belongs to 110 family. Now let's see how to get the Miller indices of planes. Let's say we want to get the Miller indices of this particular shaded plane, which is a plane shifted one unit along the x-axis and parallel to y and z-axis. Then the first step is to identify the intercepts on the x, y and z-axis. In this case, the intercept on the x-axis is at x is equal to a, but the surface is parallel to the y and z-axis. Therefore, there is no intercept on these two axes, but we shall consider the intercept to be at infinity for the special cases where the planes is perpendicular to an axis. The intercept on the x, y and z axis are thus a, infinity and infinity. Now the second step is to specify the intercepts in fractional coordinates. Coordinates are converted to fractional coordinates by dividing by the respective cell dimension. For example, a point xyz in a unit cell of dimensions a, b, c has fractional coordinates of x by a, y by b and z by c. In the case of a cubic unit cell, each coordinate will simply be divided by the cubic cell distance a. So this gives the fractional intercepts are a by a, infinity by b and infinity by c. So that will result 1, infinity and infinity. Now the third step is to take the reciprocals of the fractional intercepts. This will give us the Miller indices, which by convention is specified in brackets without being separated by any comma or other symbols. The reciprocal of 1 and infinity are 1 and 0 respectively. Thus, we get the Miller indices as 1, 0, 0 specified in normal brackets without any other symbols. So this particular plane is the 100 plane of the crystal, and you can see that the 100 direction is perpendicular to 100 plane, and this is true for all directions and planes. A particular direction will be always perpendicular to the respective planes, and you should note the difference of specifying the direction and the Miller indices of directions and planes. While we talk about the directions, we use the square brackets, but when we talk about a particular plane, we use the normal brackets. And now let's see how to draw a plane with the given HKL indices. In this example, we are going to construct the 2, 2, 1 plane. Here 2, 2, 1 is the HKL indices of the plane. So the first step is to find the reciprocal of HKL. If one or more of the indices is 0, consider the reciprocal to be infinity. The values 1 by h, 1 by k and 1 by l are the intercepts of the x, y and z axis respectively. If one or more intercept is infinity, this means that the plane will never intercept that axis, or in other words, it is a plane parallel to that axis. For the 2, 2, 1 plane, the reciprocals would be 1 by 2, 1 by 2 and 1. So next, for all non-zero indices, draw a point on the x-axis at a by h, a point on the y-axis at b by k, and a point on the z-axis at c by l. So those points are marked by these white dots on the screen. And now we just connect these points to get the required plane. So the 2, 2, 1 plane is shown by this triangular shaped plane. Until now, we were using real crystal structure to understand it. Today I will introduce another important concept in crystal physics, the reciprocal lattice. Every crystal has two lattices associated with it. One is the crystal lattice and the other one is known as the reciprocal lattice. The reciprocal lattice is a lattice in the Fourier space associated with the crystal. To know the crystal structure, the standard procedure is to study the X-ray diffraction pattern of the given crystal. This diffraction pattern of the crystal is a map of the reciprocal lattice of the crystal. If you are familiar with reciprocal lattice, you can understand and interpret the results of diffraction experiments and obtain useful information about the internal structure of crystalline matter. The concept of the reciprocal lattice plays an important role not only in X-ray crystallography but also in lattice vibrations, electronic band structure, and in fact all of the solid state physics. We have seen how to use Miller indices to specify a crystal plane. Apart from that Miller indices, any plane can also be characterized by a vector sigma HKL perpendicular to it. So let's see how to do it. I have shown a plane in the XYZ coordinate system here. This red line represents a normal vector to this surface, and let's represent it by the symbol sigma HKL, where these HKL are basically the Miller indices. Now let's consider any point on this plane like this orange dot. If you take the projection of the position vector of this point onto the normal, we will get a vector whose endpoint is exactly at the point where this sigma HKL intercepts this plane. Whichever point you choose on this plane, the projection of the position vector of that point will always be at this point. So we can see that this projection vector is obviously a constant and independent of the point that you choose on this plane. This projection is basically the distance of the plane to the origin, or in other words, this is the spacing of the plane and we represent it by the symbol DHKL. Now let's consider another plane parallel to it at a distance DHKL from this first plane. We can say that it forms a family of planes HKL with the interplanar distance DHKL. You can imagine a normal with any length to this family. Out of this, we choose a vector normal to this family sigma HKL with the length 1 by DHKL. Now you consider any point on a plane from this family, that is either on the first plane or on the second plane in this example, with position vector r from the origin. So let's assume that we have taken a point on the second plane and the projection of this position vector onto the sigma HKL is shown as d prime HKL here. So since we are considering a family of planes with the same interplanar spacing, this d prime HKL is actually 2 times DHKL, or in general such projections will always be an integral multiple of interplanar distance DHKL. So we can see that the scalar product between this projection and this vector sigma HKL is an integer n. This integer gives us the order of the particular plane in the HKL family. That is, will be 0 for the plane passing through the origin, and it will be 1 for the first plane and 2 for the second plane, etc. Thus, sigma HKL represents the whole family of HKL planes having an interplanar spacing given by DHKL. We have seen that sigma HKL dot D prime HKL equal to n, the order of the plane, where D prime HKL is the projection of any position vector to sigma HKL, and this is equal to DHKL for the first plane. So for the first plane, we get the product between sigma HKL and DHKL equal to 1. If we had chosen a normal vector sigma prime, which is 2 times longer than this sigma HKL, then the product sigma prime dot DHKL equal to 1 would imply that this new vector will correspond to a plane with an interplanar spacing half of the previous one. So that is shown here, this small plane. So in general, if we take a normal vector sigma prime HKL, which is n times longer than sigma HKL, this new vector corresponds to a family of planes of indices NH, NK and NL with an interplanar spacing which is n times smaller. Therefore, we arrive in an important conclusion that the length of the perpendicular vectors sigma HKL are reciprocal to the interplanar spacings. Now let's consider a two-dimensional direct lattice like this one with lattice vectors A and B as shown here. Let's choose an arbitrary origin. Then consider the 0, 1 plane with interplanar spacing D01. Draw a vector normal to this plane with length exactly equals 1 by D01. Let's mark the endpoint of this vector by an orange dot. Next, we consider a family of 1, 1 planes with interplanar spacing D11. Draw a vector normal to this plane with length exactly equals 1 by D11. Then mark the endpoint of this vector by a violet dot. If we do the same procedure for 2, 1 and 3, 1 planes, we get 2 more points like these red and cyan dots. Now let's do the same kind of work on 0, 2, 1, 2, 2, 2 and 3, 2 planes. So this will give us another set of points like this top row. If we join these points, which are endpoints of many normal vectors, we will get another lattice like this. Since the length of the normal vectors are reciprocal of the interplanar spacing of respective planes, this new lattice is known as the reciprocal lattice of the original direct lattice. The reciprocal points obtained in this way are identified with the same Miller indices, which represents the corresponding plane family. So a reciprocal lattice is a lattice constructed from a real lattice. However, its interplanar spacing is reciprocal of the interplanar spacing of the real lattice. A formal definition can be given like this. The reciprocal space lattice is a set of imaginary points constructed in such a way that the direction of a vector from one point to another coincides with the direction of a normal to the real space planes and the separation of those points is equal to the reciprocal of the real interplanar distance. Like in real lattice, we can define a unit cell called the reciprocal unit cell in this reciprocal lattice as well. If the unit cell axis and angles of the direct cells are represented by the vectors A, B, C and the angles alpha, beta and gamma, the corresponding parameters for the reciprocal cells are written with the same symbols, adding an asterisk, that is A star, B star, C star and alpha star, beta star and gamma star represents the lattice parameters in the reciprocal lattice space. Any reciprocal vector in 3 dimensions can be expressed as a linear combination of these 3 reciprocal vectors, that is sigma HKL can be written as a linear combination of A star, B star and C star. From the geometric relationship between the direct and reciprocal cells, we can get the relations between direct lattice vector and reciprocal lattice vectors. A star is perpendicular to B and C, B star is perpendicular to A and C, and C star is perpendicular to A and B. Hence, we can write the expressions for A star, B star and C star like this. The denominators are basically same and it is the volume of the direct lattice unit cell. Note that in accordance with this definition, the length of A star is the inverse of the interplanar spacing D100 and B star is 1 by D010 and C star is 1 by D001. Therefore, we can write A dot A star equal to 1 and A dot B star equal to 0, and similarly with other pairs of axes as well. You can actually download and execute the Java applet by Nicolas Chauny and Gervais Chapis of the Ecole Polytechnique to understand the relation between direct and reciprocal lattice and how to build the reciprocal lattice from a direct lattice. I will post the link in the discussion forum. You can get it from there. It is conventional to let the reciprocal lattice vector be 2 pi times the reciprocals of interplanar distance. This convention basically converts the units from periods per unit length to radians per unit length. Radians per centimeter are widely used units. It simplifies the comparison of different periodic phenomena. For instance, k, the wave vector, has an absolute value of 2 pi by lambda. If we choose this convention, we can compare the two values directly. All it does is expand the size of the reciprocal lattice. The relationship between the period and frequency is similar to that of the reciprocal and the direct lattice. Therefore, Fourier transformation is used in the studies of the real lattice to yield the reciprocal lattice in the same fashion as with the studies of any other periodic function. Therefore, the reciprocal space is also called Fourier space. Reciprocal space is also called momentum space or K space, especially in the context of quantum mechanics. We call this as K space because momentum, which is directly proportional to the wave vector K, is inversely proportional to the wavelength. Therefore, each point of the reciprocal lattice represents the direction and the magnitude of momentum. Now let's see how the reciprocal lattice of certain simple direct lattice looks like. Let's first consider a simple cubic system. The primitive translation vectors of a simple cubic lattice may be written as like this: A equal to AI, B equal to Bj and C equal to Ck, where the volume of the unit cell is given by A dot B cross C. Now the primitive translation vector of reciprocal lattice of simple cubic lattice will be A star is given by 2 pi times B cross C by A dot B cross C. So since it's a simple cubic system, A, B and C are equal. So you can write it as 2 pi by A into I. Similarly, we get B star is equal to 2 pi by A into unit vector J, and C star is equal to 2 pi by A into unit vector K. From these equations, it is clear that all three lattice vectors have same magnitude, and hence the reciprocal lattice to simple cubic lattice is itself a simple cubic lattice with a lattice constant 2 pi by A. Next, let's consider a body-centered cubic system. The primitive translation vectors of the BCC lattice shown here is given by these three expressions for A prime, B prime and C prime, where A is the side of the conventional unit cube and I, J and K are orthogonal unit vectors parallel to cube edges. The volume of the primitive unit cell is given by again A prime dot B prime cross C prime, which will be A cube by 2. The primitive translation vector A star of the reciprocal lattice is defined by this same standard expression. So if you substitute for A prime, B prime and C prime from the top expressions, we get A star equal to 2 pi by A into I plus J. Similarly, we get B star is 2 pi by A into J plus K and C star equal to 2 pi by A into K plus I. These reciprocal lattice vectors are the primitive vectors of a face-centered cubic lattice. Thus, you can say that the FCC lattice is the reciprocal lattice of the BCC lattice. Next, let's consider a face-centered cubic lattice. The primitive translation vectors of the FCC lattice is given by again these three expressions A prime, B prime, C prime, where A is the side of the conventional unit cube and I, J, K are orthogonal unit vectors parallel to the cube edges. The volume of the primitive unit cell is given by A prime dot B prime cross C, which will be A cube by 4. The primitive translation vector A star of the reciprocal lattice is defined by the standard definition, and if you substitute for A prime, B prime and C prime, we get it as 2 pi by A into I plus J minus K. Similarly, for B star we get it as 2 pi by A into minus I plus J plus K, and C star equal to 2 pi by A into I minus J plus K. These reciprocal lattice vectors are the primitive vectors of a body-centered cubic lattice. Thus, the BCC lattice is the reciprocal lattice of the FCC lattice. Before concluding this section, let's quickly revise the important properties of a reciprocal lattice. Every reciprocal lattice vector sigma HKL is normal to the plane of the crystal lattice. The interplanar spacing DHKL in a real crystal lattice is equal to 1 by sigma HKL. The reciprocal of the reciprocal lattice is a direct lattice. Volume of the unit cell of the reciprocal lattice is inversely proportional to that of the corresponding direct lattice.